That's how I touch them. It's okay. It's always the cool glasses.
So if you could draw if you're working on that worksheet, just kind of hold off for a minute. This won't take long at all. I don't think that this particular portion, I've been wrong hundreds of times before, but we're going to do a lot of stuff with trigonometric graphs with the sine and the cosine. We'll eventually start tweaking the tangent, but we still haven't even really formally talked about the tangent curve. So we're going to stick today and probably Monday with just sine and cosine. You know what they look like. You know how they undulate up and down like that. So what we're going to spend a few days doing is just tinkering with those graphs. I decided to do the first two, what we call transformations out of the way today. Graphs can be transformed in a ton of different ways. One way is you can physically move the whole graph up and down. Another way is you can shift it sideways. Another way is you can actually stretch it out or compress it horizontally. And another thing you can do is stretch it or compress it vertically. The two easiest ones with these graphs, with any graphs, I think, are the vertical stretch. That's called amplitude. You've heard that word before, probably in science. So when you talk about like a sine curve and a cosine curve, they have amplitude. And the amplitude of a curve is defined as the distance from its horizontal center. We call that the midline. You're going to hear me say that a lot. So the distance from the midline to the highest and lowest points is called the amplitude. So like, for example, the graphs we did yesterday, we didn't accomplish a ton, but I felt like it was still productive. We sketched a sine curve and a cosine curve. What would you say is the amplitude of the sine curve? It is 1, because from the midline to the highest point is 1, or vice versa, from the midline to the lowest point is a distance of 1. What's the amplitude of the cosine curve? Also 1, right? So those functions, default versions, unmodified versions, have amplitudes of 1. The other thing we're going to modify today, so we are going to modify amplitude, by the way. So if you'll see it on the worksheet, but I'll put it up here on Desmos, there's a certain place where you can put a number and it actually keeps the graph, it keeps the length of the period the same, keeps the midline the same, but it takes the highs and stretches them and takes the lows and stretches them. That's called an amplitude adjustment. So that's really easy to do. The other one we're going to do today is we're going to move the midline up and down. And I don't know if you remember this like from Algebra 1, because it's been a minute. But if I gave you a graph like 4x, well, let's even make it less steep than that. Let's do like 1/3 of x. Like this. So there's a simple graph, right? If I wanted my class, like my 9th graders just learning how to graph lines, if I wanted them to physically graph the same line, same slope, same physical structure, but I wanted them to move the graph up 4, then I would have them simply put a modifier at the end, like +4. And then you can see the graph literally picks itself up and moves itself up. Making vertical adjustments is a cakewalk. You literally just add a number or subtract a number after the meat and potatoes part of the function has happened. So when we talk about like trig functions, sine of x is the meat and potatoes part. That's where all the math is happening. And then if you throw in like an afterthought, like a +5, then the whole flipping graph just goes up 5 units, or vice versa for down. So that's what we're going to talk about. Vertical adjustments, super easy. Amplitude, I also think pretty easy. And then your job, and you don't have to get this done today, but we're going to at least get started. Our job is to, on that next assignment, we're going to sketch 8 graphs, and the modifications to them will be amplitude adjustments and midline adjustments. I'm telling you, this gets a trillion times more difficult next week when we start stretching and compressing the length of the period. And then you do something called a phase shift, which sounds all scientific and stuff. But when you do a phase shift, you actually horizontally move the graph. And if you do that while doinking around with the period, it's a lot. There's a lot of meat on that bone. So we're going to get these two simple ones out of the way today. So let's take a look at just a simple sine curve. So if I looked at like sine of x, you know this guy from yesterday, right? I'll zoom in a little bit so you can get a good look at the, and I think I can change my axis to radians. Oh, I think it's already in radians. X-axis, whatever, good enough. So that's just a typical sine curve, huh? What do you think is something I could do to modify its amplitude? And by amplitude, what I mean is I want the graph to be taller at its tall points and lower at its low points. What's something in math I can do to make that happen? If I add a number at the end, I want you to see what happens. So I'm going to type in right below it. I'm going to do sine of x plus, say, 1, and I want you to see what happens. Did I make the graph taller and lower? Did I stretch it? No, I moved the midline, right? So what Brady just said is great, but that's going to be in a minute when we talk about the midline. And I did hear it from over here. Let's try a different kind of modification. Let's go back to the sine of x and let's throw a number in the front, like 2. Watch what happens now. We did it. By multiplying the entire meat and potatoes part of the function, like the business end of the function, by 2, you've taken all of the y values and forcefully said, I want you to be twice as exaggerated. So like at the highest point, right, I don't know if you can see where I'm moving my mouse, but like right here, can you see that? What's that highest blue point? That was 1. What's this one? Perfect. So making an amplitude adjustment is an absolute cakewalk. You just multiply by a scalar, like 2 or 3 or 4, and you can, of course, use fractions. Hint, hint. So having said that, how do you think we could take our standard up 1 to down 1 sine curve and make it shorter with a fraction? So for example, if I took the sine of x, but I slapped like a 1/3 in front of it, what happens now is all those y values that were previously whatever they were before are now 1/3 as big as they were before. This is a really common transformation to make on a graph. It's just a vertical squish or a vertical stretch. And in this particular case, we specifically call it amplitude. Sine and cosine curves. Amplitude is the big word. Do you have any questions about that? The question becomes, how do I graph this by hand? Well, my take when I was learning trigonometry was I'm going to start by fixating on the ones that are simple. To me, the simplest ones for anyone to understand. What's nice about sine and cosine is they always return home. 4 times you're going to hit those home bases where you have like a 0 or a 1 and a 0 or a 1 and a 0 or a 1 and a 0 or a 1, right? So the zeros don't change. Because when you multiply 0 by 2 or 3 or 4, who cares, right? So that's like a home base that I can always use when I'm sketching a curve. And then I have my highs. So like if the sine curve normally goes up to 1 and you give me an amplitude adjustment of times 3, where am I going to go to? I'm simply going to go up to 3. And then that's at least a couple of dots for me to play connect the dots with. And usually people would tell you that's really not enough. So how can I find a point in between, say, those? Multiply, use the death out of your calculator. Like we know, so let's say we were just screwing around and we were doing a normal sine curve. You know that between 0 and pi over 2, where sine goes from 0 to 1, halfway there's a stop. And we used the death out of it yesterday. Do you remember what the root 2 over 2 is as a decimal? 0.7. We use that a lot. So if we're scaling our graph up, say times 3, then I can just take that decimal value, triple it, and head up to like 2.1. Am I making any sense at all? The key is you got to have those home base, those numbers they're your anchors. The unit circle numbers are our anchors. Everything else is founded or discovered or obtained by doinking around with the numbers that I just quizzed you on, the numbers that you've hopefully got memorized pretty well. Right? So let's practice doing a graph by hand with only an amplitude modification. Okay, so that would be, as if you want an example of that, that would be one of the problems on your first page. Right? So let's take a look at one of those. And I'll get my board is somewhere. It's probably, I got so much stuff on my desk. Which one do you want to do? You pick 1, 2, 3, or 4. We're only going to do 1. So number 2 it is. Oh, I heard them change their mind. We're going to do 4. So let's do 4. So, because 2's already on the TV. So let's get rid of that. What? Say who? All done? Do you feel good?
Yeah.
Oh, I felt good about it the first time, but then I'm like, oh, that's not what I
You're welcome to stick around. We're gonna graph some curves.
I'm gonna do my notes.
Sounds
Yeah.
good. You're welcome anytime. Good to see you.
Four's on the board. Yeah.
4 is not on the board. So that's all you got to know. And that'll get us through a lot of questions that we have. The question, in case you didn't hear it, was the difference between sine and cosine is, and the statement was completed by saying one starts high, one starts low. Like that's huge. So having that separation in your mind is going to be critical. And
Is it extra?
cosine starts high and sine starts at 0. So the cosine and sine, by the way, they both have the same midline. So I'm going to graph a red line up here. And it's going to kind of get in the way. But that red line is called the midline. So whether we graph sine or cosine, our graph is going to like snake around that line. It'll symmetrically go above it and then below it by the same amount, right? So if we want to graph number 4, and number 4 says that y equals f of x equals whatever, same div, same. So we have y equals double the cosine of x. So the key here, or cosine of theta, you're going to start seeing like alpha, beta, theta, because since we're using angles, angles are often referred to not as xe values, but as like Greek letter values. And theta is a super popular one in trig land. So FYI. So theta, 2 times the cosine of theta. So if theta is 0, you okay?
Yeah.
Is that bothering you, the theta? Theta, theta? You thought I said theta? Yeah, that's why I spelled it out. Theta.
I was looking for it on the board.
It's over there. It's just hard to see with those lights and the glare. But yeah, theta is a letter of the Greek alphabet. As is alpha, as is beta, gamma. You're going to see all that.
Except I was in the corner.
So nice little detour there. Anyhow, let's get back to it. As far as you're concerned, theta is just an independent variable. It's no different than x, okay? We feed theta, function gives us back y. That's how functions and equations have always worked. So if I'm at 0, if I haven't started my journey yet, so let me put some stuff in to kind of, I can't match you perfectly, but I think your graph paper has 1. It goes by ones, doesn't it? So I kind of can match you perfectly. Never mind. So your graph paper looks like this. So listen, the first thing I'm going to graph is the default. Don't do this. I'm just going to do it. If someone said to me, hey, start graphing me the cosine of theta, my first point would go right here. Do you see that? I know it's small, but do you see? Because cosine starts at 1. And if you don't remember that, just go back to your unit circle. If you're at 0 at the beginning of the unit circle, the cosine is 1. You know that, right? So that's how we can remember that cosine starts high. Now cosine begins his travels. And as we head to the next, let's go to the next stop along the way, pi over 2. And I'm just looking at your graph paper like your assignment. Pi over 2 seems like a nice place to go. What is the cosine at pi over 2? It's 0. Okay, so I'm just graphing the default right now. I know I've already said that, but the default is, oh, and I should have skipped it because you guys have to skip a line. So my bad. I'll make it look just like yours. So yours should go like that. And then the next one that's labeled is pi, right? What's the cosine at pi? -1. So now we're over here. And then what's the next one? 3 pi over 2. What's the cosine down at the bottom of the unit circle? We're back to 0. And then what's the cosine at the last one, 2 pi? So 2 pi, we're back up to 1. And then your graph does go longer. We go to 5 pi over 2, which is, of course, just continue around the circle now. There's no stopping us. We're headed back up. This is coterminal with the old pi over 2. Top of the unit circle, what's our cosine? We're back to 0. And then the last one is 3 pi, which you understand is coterminal with left side, which is -1. So here are the dots that I would have if it were just a regular cosine. We're going to buff them. We're going to buff the highs and we're going to buff the lows. So the actual graph, guys, you should have a dot up here at 2. Your 0 should still be the same. Your -1 should be buffed down to -2. Your 0 should stay the same. Your 1 should be buffed again up to 2. 0 stays, -1 buffs. That's an amplitude adjustment, and that's how easy it is to make. Do you have to graph the original points? Of course not. I think it's just a good kind of starting off point for us. And then, of course, this is not a graph yet. This is just a bunch of points. And so what we're going to do is we're going to now try to make it look like we care about our graph. And we're going to sketch a curve. Try to make it smooth. Try to make it look like you're always turning, you know? You shouldn't have any straight lines when you graph a trig function like this. So there is what number 4 should look like for you. Are you with me? No, I really could use a little feedback. Is that okay? Marvelous. So the only thing that we're probably not going to get to, but I want to say it here in about I got about 2 minutes and 12 seconds. So I want to say a quick thing and then we'll pack up. What's going to happen when we get to the next page is we're going to just literally pick up the whole graph and move it. And it is a little bit more complicated than just amplitude adjustment. But like you see how the graph is symmetric about the red line. So it makes sense, I would hope for you, that if the red line were to say move up, then all of the points move up proportionally, don't they? If red line goes up 3, then every other point goes up 3. But the distance between the red line and the highs and the lows is still dictated by the amplitude, huh? So we'll cross that bridge on Monday. I don't want to try to hustle through one of those. So you don't have to. No, that's okay. We'll work on it Monday.